Hi, you guys. Today I have problem 4.33 from Young and Freedman's University Physics textbook. Before we get started, if you find any of my videos helpful, please don't forget to like and subscribe and share with your friends. Yeah, and if you don't, then, if you don't like my videos, then I'm sorry. I hope that you stick around and you find something helpful. Okay, so let's do the problem. A 5.60 kilogram bucket of water is accelerated upward by a cord of negligible mass whose breaking strength is 75.0 newtons. If the bucket starts from rest, what is the minimum time required to raise the bucket a vertical distance of 12.0 meters without breaking the cord? Okay, so let's go ahead and just write down all of our knowns because I can see that we just have a lot of knowns. So knowns, a 5.60 bucket of water. So the mass of this bucket is 5.60 kilograms, is accelerated upwards, okay, by a cord of negligible mass, okay, whose breaking strength is 75.0 newtons. So let's say Ft. So I wrote, actually, you know what? I shouldn't use T because T is usually used for tension. So I'm just going to go ahead and say F. Okay, let's do string or cord. Actually, that's a good one. There's usually no FC. Okay, so FC, that is equal to the breaking strength of the cord, right? So breaking strength of the cord is 75.0 newtons. If the bucket starts from rest, so VI of bucket is equal to 0 meters per second. What is the minimum time? So we're looking for time. We don't know what time is. To raise the bucket a vertical distance of 12.0 meters. Okay, so now let's actually try to understand this problem. We have a bucket, and sorry, as we understand it, we're also going to go ahead and draw it. So we have this bucket. Okay, so let's draw this little bucket. And it is being accelerated upward. Okay. And by a cord whose breaking strength is 75 newtons. So there's going to be some sort of cord. I'm going to change color just so that it's a little bit clear to us. So we have this cord right over here. And obviously this cord is attached to something. So it doesn't really matter what, but it's attached to something. And if the bucket starts from rest, right? So it's starting, from this point right over here, and we want to raise it a vertical distance of 12.0 meters. Okay, so we want to raise it some distance 12 meters, and we don't want this cord to break. So how long will this take? Okay, so before we actually get to solving the question, I think it would be really helpful if we go ahead and draw like a little force body diagram. So one thing that I like to do in the past, I have sort of used boxes to draw force body diagrams, but I think that I'm going to go ahead and just use a little dot because I think sometimes I just like to pretend things are point sources, or not even a point source, but like just the mass is a central point. Okay, so this is the bucket, just to make that abundantly clear. That's the bucket, but I'm going to go ahead and erase that because I don't want a messy drawing. All right, so this bucket has some forces acting on it. What forces are acting on it? While assuming that we're on planet Earth, which, there's no indication that we're not, there's going to be some sort of force of gravity, right? Or I shouldn't say some sort of force. There is a force of gravity. So Fg, downwards, right? Then there's going to be some Ft, and that is going to be upwards, right? And that's really it, right? Those are the only forces that are acting on it. All we know is that to raise the bucket, F net is going to be upwards, right? And while we have this little diagram, let's go ahead and say that this is going to be positive and this is going to be negative, right? So this breaking strength of this cord, I guess this is a good place to note that this breaking strength of the cord is going to be the tension, right? So this Ft is equal to Fc. That's not really a big deal, to be honest. Now that I'm thinking about it, we could have also just called this FT, but whatever. It doesn't matter what you want to name it. You want to name you can literally give your forces any name you want. I'm not judging. Okay. So now that we have our diagram, let's go ahead and just write down an equation for this diagram, right? So equations to sort of describe this motion. So the net force, right? So the total forces that are acting on this, it's going to be the F net, right? So it's going to be moving, or sorry, the summation of forces. Actually, I shouldn't say that. You know what? Let's say it this way. So the summation of forces are going to be FT, right? Because FT or FC, right? So this force going upward, it's going to be that force minus FG, right? Because that's going downward. And altogether, that's going to be the net force. That's going to be F net, right? So that makes sense. All right. Now let's look for what the question is actually asking. We are looking for time. So minimum time, right? Okay. So if we want to know, the minimum time that it takes, and these are the pieces of information that we have, what we want to do right now is, sorry, give me 1 second. Sorry, every time I get a text, I get so distracted and then I just can't focus. So now you have my undivided attention. Okay, so now the next step that we need to do is that, okay, so we have our equations. What we can do now, because we want to find minimum time, let's just flesh out our equations a little bit better and see if we can find time within these variables, right? So FT or FC, like we have that right over here. So we're not really going to find time there, right? FG, that's just, let's put it this way. Let's rewrite this equation. So F net is equal to FT, which we have, minus FG, which is, just mg, right? So we have mass times gravity. So we have mass, we have gravity. So we're not really going to find FT in this portion. Now, F net. So isn't F net, can't we rewrite that as the mass times the acceleration, right? So F net is going to be the mass times the acceleration of the system. Okay, we're sort of getting somewhere, because isn't acceleration, can't we use, VI, D, and sorry, I didn't even write D over here. Okay, so we can use VI, we can use D, we can use A to find T, right? So if that's true, then all we really need to do is we need to solve for A, and then we can use A to solve for T using D and VI, right? Because then this just becomes a quick one-dimensional kinematics problem, right? We can just use one of the 5 kinematic equations and we can solve for T. Okay, so now FT, or okay, sorry, let's solve for A. So A is going to be equal to FT minus mg over m. And we already have all these values, right? So FT is 75 newtons minus mg, which is 5.6 times 9.8, and that's going to be divided by 5.6. So the acceleration, I'm just going to plug that into my calculator. I do these problems beforehand, but just really quickly and roughly, and I just want to make sure that I'm not making any mistakes right now. Okay, so acceleration I'm getting is 3.593 meters per second squared, right? So that is what I'm getting for the acceleration. And now that we have acceleration, what we can do is use acceleration, right? Use distance or displacement, or yeah, distance, I guess, and use VI to solve for T. And how are we going to do that? Well, using this equation right over here. D is equal to V naught T plus half of AT squared. Remember our equation that we use in every single video, or almost every single video. Okay, anyways, so what we're going to do is now we can plug everything in and just isolate for T. So VI, no, that's 0, so we can just cancel out this term. And now it's going to be D is equal to half of AT squared. Now it's going to be 2D divided by A is equal to T squared. And T is just going to be root of 2D over A. And that is going to be, we're going to plug in our values. It's going to be 2 times 12, 2 times 12 divided by 3.593, and then square root that. And when I do that, what I get is that T is equal to 2.58 seconds. And sorry, this problem is so messy, but I think you can follow along. And if not, just rewind and follow along then. Sorry, I'm distracted again. But yeah, so the time that it would take is going to be 2.58 seconds. Okay, so I want to try something a little bit new in this video. Now, one question you might have is, well, let's do a little bit of investigating or a little bit of exploratory work and see what will happen if the time is greater than this or if it's smaller than this, right? So, well, from the question, we can tell that the minimum amount of time means that if we go above this time, so if we take longer than this, it should be fine. The force of tension should be low, and the cord won't break, right? But again, judging by the wording in the question, we can infer that if the time is smaller than 2.58 seconds, then what's going to happen is that this cord is going to break. So let's just look at both situations. Okay. All right. So sorry, I said all right because I just took a picture of all the knowns and everything just because this page is so messy and I'm going to erase everything. So let's go ahead and try that. If we have, so let's assume that the time is going to be, well, we know that the time is 2.58 seconds. That is officially the answer, but let's see what happens at t is equal to 1.0 second and t is equal to 3.0 seconds. Okay. All right. So what we need is, if we want to find out what ft is, right? Because we need to know if it's greater than this or smaller than this, what we can do is we can sort of, reverse or we can use our equation from before. So before we said that F net is equal to Ft minus mg, and F net was really just, ma is equal to Ft minus mg, and we're looking for Ft, so it's going to be Ft is equal to ma plus mg. And we can rewrite this as m is equal to a plus g. And just double checking to make sure that this all makes sense. And yep, it does. Okay, perfect. So we're going to go ahead and use our knowns for VI and our knowns for VI, D, and T, right? To find what acceleration is. And then using that, we can plug that back in and see what Ft is going to look like. So Vi, we said, is going to be 0, and D well, according to the question, it's 0 right now. We didn't say that. We know that from the question. Then D is going to be 12.0 meters, and the time is going to be 1.0 and 3.0. So let's look at acceleration. One is going to be 1.0. What's that going to be an acceleration when? Actually, I should rewrite that a little bit better. We should say this. So acceleration when the time is 1.0 and acceleration when time is 3.0 seconds. So what is that equal to? Again, we're just going to use our equation, which was, sorry, just pulling it out again. Okay, so our equation was, again, this. So D is equal to V naught T plus half of AT squared. And we're just going to isolate for A, which is going to be 2D over T squared. So the first one, right, it's going to be 2 times 12 divided by 1.0 squared. And then for the other, it's going to be 2 times 12 divided by 3 squared, right? And you know what, I'm going to use blue just so that everything's a little bit more, not cleaner, but more organized. 2 times 12 divided by 1, that's going to be equal to 24. So acceleration is going to be 24 meters per second squared. And for the second one, it's going to be 2 times 12 divided by 9, which is going to be, just going to double check that, 24 divided by 9. Yep, 2.667 meters per second squared. So automatically, we can see that we need a low acceleration not to break this chord. And the faster that we raise this, the higher the acceleration is going to be, which the chord can't handle. Okay, so Ft, when at t is equal to 1.0, is going to be mass, which is 5.60 times 24 multiplied, sorry, not multiplied, plus 9.8, right? And Ft at times equal to 3.0 seconds is equal to 5.6 times 20, no, not 24, 2.667 plus 9.8, right? Because gravity from here. And when we plug those values in, for this one, I'm getting the tension of the cord is going to be 189.28 newtons. That's going to be the tension in the cord and will obviously break when the time that it takes to raise this bucket takes 1 second. And then with 3, it's going to be 2.667 plus 9.8 times 5.6. And the total I'm getting is 69.82 newtons, right? And yeah, automatically we can see that the slower this bucket is raised, the smaller the force of tension is. And you know what? Just looking back at our equation, and I guess our equation for time, right? So in the last slide, we said that t was equal to root of 2d over a. So actually, you know what? I'm not going to go into that. Sorry, give me a second to think about it first. Actually, you know what? No, never mind. Okay, let's ignore that. Let's just leave it at this. I did this as a fun exercise. If you find it helpful to understand the question, that's great. If not, then you can just ignore this part. It's really not part of the question. The first part of the question, the first part of the problem that I solved on the last slide, that was everything that was part of the question. So I hope that this video was helpful. If it was, please don't forget to like and subscribe. As always, you can reach me by email or through the comments. Thank you so much for watching and see you next time.